train's large momentum caused by their enormous mass and high speeds means that stopping them in time can be a serious challenge. In 2019, there were 1,516 railway accidents in the EU. But how do engineers and train operators keep trains from hitting one another? Trains are uniquely susceptible to collisions as they travel on fixed rails and are unable to maneuver to get out of the way of another approaching train. Not only that, but trains' large momentum caused by their enormous mass and high speeds means that stopping them in time can be a serious challenge. That's before you even factor in the issue of human response times and errors of judgment. History is filled with examples of tragic collisions. One of the worst ever in history occurred in 1918 in the United States. Known today as the Great Train Wreck of 1918, a head-on collision between two trains speeding at 80.5 kilometers per hour resulted in the deaths of at least 101 passengers. Later investigation discovered that the cause was human error, as one of the train's engineers failed to adhere to written right-of-way rules. Sadly, many other examples exist throughout the history of trains. In fact, train collisions still happen today. In 2019, there were 1,516 railway accidents in the EU, but fewer than 10% of these were collisions. But how do engineers and train operators keep trains from hitting one another? Some of the earliest attempts to prevent train collisions came in the form of the 1889 UK Regulation of Railways Act. This piece of legislation sought to introduce a series of safety measures, like interlocked block signaling, to avoid disasters like the Armagh Rail disaster, which killed around 89 people that very same year. But these early measures still relied on human operators. Since most train accidents are caused by human error, one solution might be to remove human operators altogether. This is exactly what some rail projects around the world are currently exploring. Many rail lines and even mass transit systems are already semi-autonomous or even driverless. In 2018, the International Association of Public Transport found that 42 cities were already running automated metro lines. In 2019, the Anglo-Australian mining giant Rio Tinto launched the fully automated heavy-haul rail system in the Pilbara region of Western Australia, the world's first fully automated mainline rail network. Some French operators like SNCF are also working to develop prototypes for remote-controlled, locomotive-hauled autonomous trains by 2022. However, progress in this area is often slowed by unions and other vested interests. If humans cannot be fully removed from the equation, is there anything else that can be done? Various safety systems have been developed and implemented in the past, which make use of trackside sensors and base stations to provide various data, such as location and speed. But these tend to be very expensive and often rely heavily on human operators to do something about an impending collision. Since we are still seeing regular collisions around the world, these kinds of systems are clearly not foolproof. Until fully automated trains become widespread, is there anything else that can be done to reduce or eliminate train collisions? It turns out there just might be. One interesting development comes from India. Indian Railways has developed a traffic collision avoidance system. The automatic train protection system is being tested on a track between Umri and Sivunjan stations in the Nanded district of Marathwada. Systems like this might provide a useful stopgap until more global train networks become fully automated. Similar systems already exist in the aviation and shipping industries. However, unlike these industries, trains need to pass within meters of one another when on parallel tracks. This requires pinpoint accuracy and control. The Indian system relies on GPS satellites to constantly monitor train positions. Each train exchanges pertinent information between each other to automatically calculate the chances of a collision and engage the train's brakes in enough time to avoid collision. When an impending potential collision is detected, the system reduces the train's speed in preparation for a complete stop. By doing this, it helps to prevent collisions when trains are traveling on parallel tracks, at level crossings, on approaches to stations, and at other locations where train collisions are most common. Current experiments with the system have proved to be very promising, and plans are in place to roll it out to other tracks in the area. Other similar systems are also in use or development in other parts of the world. Notably, the Rail Collision Avoidance System in Europe, RCAS, uses onboard GPS data to work out what stretch of track a train is traveling on and can determine whether it is on the left or right-hand track. This information is then broadcasted directly to other trains within a 5-kilometer radius, and the system builds a map of the track as it travels. The benefit of RCAS is that it complements existing technologies to improve safety and doesn't rely on existing equipment. Moreover, it can be fitted to any train. As systems like TCAS and RCAS become more sophisticated and trusted, we may see widespread rollout across railways around the world.